In this video, I'm going to give you a basic introduction into unit cells. Now, there's three structures you need to be familiar with. The first one on the left is the simple cubic structure. The second one in the middle is the body-centered cubic structure. And the last one is the face-centered cubic structure. So each of these cubes represent a single unit cell. And for the simple cubic structure, within one unit cell, there's only one atom. For the body-centered structure, you have 2 atoms per unit cell. And for the face-centered cubic structure, there are 4 atoms per unit cell. The coordination number of the simple cubic structure is 6. I'm going to run out of space, so I'm just going to write C equals 6. That's the coordination number. The coordination number is the number of atoms that's attached to a single atom. So every atom in the cubic structure is attached or adjacent to 6 other atoms. For the body-centered cubic structure, the coordination is 8. If you look at the atom in the middle, you can see that it's attached to 8 other atoms. This is 1, 2, 3, 4, 5, 6, 7, and the 8th one is in this other corner that you can't see based on the way it's drawn. The coordination number for the face-centered cubic structure is 12. Now the next thing we need to talk about is the volume. About 52% of the volume of the cube actually consists of the volume of the atoms in this cube. So 48% is empty space. For the body-centered cubic structure, it's 68% efficient. So what that means is that out of the entire cube, the atoms are arranged in such a way that they occupy 68% of the total space in the cube. So that means 32% is unused space. Now the face-centered cubic structure is the most efficient cubic structure. The percent by volume is 74%. So the way the atoms are arranged, they're arranged in such a way that they take up the most space. They're maximizing the use of the volume of the cube. So only 26% is empty space in that structure. So that's why it's also known as the cubic closest packing, because it's the most efficient use of space when the atoms are arranged in the face-centered cubic structure. Now the next thing we need to talk about is the edge length. The edge length I like to call X. Now other textbooks might use different letters, but X is basically the side length of a cube. So that's the edge length. R is the radius. So this is the radius. And for this structure, this is the radius here. Now for this sphere inside, this is the diameter, which is twice the radius. And here, this is R. This is 2R, and this is R as well. Now, what you need to know is the relationship between the edge length and the radius, that is the atomic radius, of the atoms in each of these structures. For the simple cubic structure, X is equal to 2R. So what that means is that the edge length is twice the value of the atomic radius of the atoms in that structure. Now if you want to visually see it, here's another R. So therefore, this whole thing is X. So X is 2R. Now for the body-centered cubic structure, the edge length, X, is equal to 4 over root 3 times the atomic radius. Now this information is useful if, let's say, you're given the density of an element and you want to find the edge length or the atomic radius of that element. And they'll have to specify which structure you're dealing with. Sometimes you might be given the atomic radius and you need to calculate the edge length in a certain cubic structure as well as the density of the material. So I'm going to go over some example problems on that in a different video. Now for the face-centered cubic structure, the edge length is equal to the square root of 8 times r. So you may want to write this information down if you have a test on this stuff. Now let's go over the simple cubic structure. Let's focus on this structure and the details that we mentioned. Now we said that there's one atom per unit cell. So here's how you can get that answer. What we need to realize is that in a simple cubic structure, there's 8 atoms that's at the edge of the cube. Now notice that we don't have a whole atom, but each atom at the edge is 1/8 of an atom. And so 1/8 times 8 is equal to 1. And that's why there's only one atom per unit cell in the simple cubic structure. Now, why is the coordination 6? Well, if you focus on one atom, there's going to be another atom above it and another atom below it. There's going to be another atom to the right and another atom to the left. Or you could say this is east and this is west, or basically just the x direction. And let's call this the z direction. Now there's also another atom in the y direction as well. So therefore, every atom is surrounded by 6 other atoms, and that's why the coordination number is equal to 6 for the simple cubic structure. Now, as we already mentioned, the edge length is 2 times the radius of the atom. So let's call this r, and this is r, and the edge length is equal to x. So this side is x and this side is x. The volume of a cube is length times width times height. So it's going to be x times x times x. So therefore the volume of a cubic structure, or the entire cube, is x cubed, is the edge length raised to the 3rd power. But each edge length is equal to 2r. It's twice the atomic radius. So make sure you remember this equation when dealing with simple cubic structures. Now the last thing we need to talk about is the volume. We said that the atoms in the simple cubic structure only use 52% of the volume of the entire cube. Now to get this ratio, or this decimal value, which is 0.52, you need to take the volume of the atoms in the unit cell and divide it by the volume of the cube. So there's only one atom per unit cell, and the volume of a spherical atom is 4/3 pi r cubed. The volume of the cube is always going to be x cubed. So what we need to do is replace x with 2r. So we're going to have 4/3 pi r cubed divided by 2r raised to the 3rd power. So that's 4/3 pi r cubed. 2 to the 3rd is 8. And then this is going to be r cubed. So you can cancel r cubed. Now 4/3 pi, that's 4 pi over 3. As a decimal, if you want to write it, it's 4.1888. And then divide that by 8. If you do that, this will give you 0.5236. So 52.36% of the volume of the cube is basically the volume of the atoms that are in the unit cell. So that's how you can get this value. Now let's talk about the body-centered cubic structure. So we said that there's 2 atoms per unit cell. Now you need to realize that every atom at the corner is 1/8 of an atom. Now we know that there's going to be 8 corners to deal with. This is number 1. Let me use a different color. That's the first corner. This is the 2nd, 3rd, 4th, 5th, 6th, 7th, and the 8th one is in the bottom left, if you were to extend this picture. So it's going to be 1/8 times 8. and then don't forget the atom in the middle. So that's one whole atom. So 1/8 times 8 is 1 plus 1, it's 2. And that's why we say that there's 2 atoms per unit cell in the body-centered cubic structure. Now the coordination number is 8, and as we mentioned before, it's easy to see that. This atom at the middle is attached to 8 other atoms, which is basically the 8 corners. 1, 2, 3, 4, 5, 6, 7, and the other one that you don't see, which is supposed to be there. So the coordination number is 8. Now let's calculate the volume of the body-centered cubic structure, at least the ratio of the volume used by the atoms relative to the volume of the entire cube. However, before we should do that, we need to talk about the edge length. Now we said that the edge length is 4 over square root 3 times r. So let's see how we can come up with that figure. Now for the body-centered cubic structure, what you need to realize is that this is r, and from here to here is 2r, and this is another r. So let me just redraw this so you could see what I'm talking about exactly. So here is the sphere in the middle, and then here's the sphere at this edge of this cube, and here's the other sphere. So this sphere, that's twice the radius, that's the diameter, and then this is r, and this is r. So the distance between the bottom edge of the cube and the top edge, that's 4r. That's what we need to realize for the body-centered cubic structure. So the longest diagonal of the cube is 4r. Now let's see how we can relate that to the edge length of the cube. Now we know that every side of the cube is equal to x. Now let's call the diagonal between these 2 points. Let's call it L. That's different from the diagonal that we want to find, which is here, that's D. So notice that this is a right triangle. Hopefully you can see the right triangle. The right triangle is at the bottom face of the cube. And so therefore we can say that L squared is equal to x squared plus x squared. So now we need to draw another right triangle, which has L as the base. This is the next hypotenuse. One of the legs is x, and the hypotenuse of this triangle is the longest diagonal D. So focusing on the triangle in green, we can see that L squared plus x squared is equal to the hypotenuse of the triangle D squared. So in this equation, we need to replace L squared with x squared plus x squared. And so we're going to get this equation. L squared, which is x squared plus x squared, and then plus this other x squared, that's equal to d squared. So 3x squared is equal to d squared. Now if we take the square root of both sides, the square root of 3 times the edge length x is equal to the length of the diagonal. And the length of the longest diagonal, we can see that it's 4r. So root 3x is equal to 4r. So solving for x, we need to divide both sides by the square root of 3. And so the edge length, I'm not sure what happened there, the edge length is 4 over root 3 times r. So that's how you can relate the edge length to the atomic radius of the atoms in the body-centered cubic structure. So now we can calculate the volume that's used up by the atoms relative to the volume of the cube. And we said it was 68% for the body-centered cubic structure. So let's confirm it. So let's find the ratio of the volume used by the atoms divided by the volume of the cube. Now we said that there's 2 atoms per unit cell. So it's going to be 2 times the volume of a sphere, 4/3 pi r cubed, divided by the volume of a cube, which is x cubed. So now what we need to do is replace x cubed with 4 over root 3 r raised to the 3rd power. So feel free to pause the video and simplify that expression. Show that is equal to 68%, or 0.68. So what I have is 2 times 4 times 1/3. That's basically 2 times 4/3 times pi times r cubed. Now 4 to the 3rd power is basically 3 4s multiplied to each other. And then I have a square root of 3. I basically have 3 of them. But whenever you combine 2 radical 3's, it's simply equal to 3. So 2 of them will change into a 3, so I have 1 root 3 left over. And then I also have r cubed. So I can cancel r cubed, I could cancel a 4, and I can cancel a 3. So what I have left over on the top is 2 pi. On the bottom, I have 4 times 4, which is 16, divided by root 3. So now I'm going to multiply the top and the bottom by root 3, so that these will cancel. So then the answer is 2 pi times root 3 divided by 16. Now let's multiply 2 pi times root 3, and that's 10.8828, and then divide that by 16. So this will give you 0.6802, which is basically 68%. So 68% of the volume of the cube is occupied by atoms. And as you mentioned before, the other 32% is the empty black space that we see here. So that's all you need to know for the body-centered cubic structure, at least for now. Now let's move on to our last structure. That is the face-centered cubic structure, also known as the cubic closest packing structure. Now this might be abbreviated as FCC. The body-centered cubic structure is abbreviated as BCC. Now we said that the volume ratio, or the volume efficiency, is 74%. So that's why it's the cubic closest packing structure. It's very efficient in using the space of the cube. Now we said that there's 4 atoms per unit cell. Now let's see how we can actually come up with that figure. Now just like the other examples, the 8 corners all contain 1/8 of an atom. So don't forget this corner and the one in the back. So that's going to be 8 times 1 over 8. Now notice that you have a sphere here. Now what this really represents is half a sphere, not a whole sphere. The way I drew the structure, it really doesn't show the entire sphere. But if I drew it like more accurately, it would represent half a sphere. Now you only see 3 of those spheres, but there's actually 6 due to the 6 faces of the cube. So it's going to be 6 times 1/2. So 8 times 1 over 8 is 1. Half of 6 is 3, so 1 plus 3 is 4. And so that's how you come up to 4 atoms per unit cell. Now I want to show you something. So here's a cube, and there's 6 faces in the cube. So we have half a sphere at the top of the cube and at the bottom of the cube. We also have it on the right side, as shown here, and also on the left side. And then we have it in the front and also the back. So here's it in the front and in back as well. So that's why we have 6 1/2 spheres. Now the coordination number is 12. Now let's think about how we can actually get that figure. Now, before attempting this, I recommend that you go to Google Images, type in face-centered cubic structure, and just look up the exact drawing of what you see here. Now, this blue sphere that you see here, I'm going to focus on that sphere. It's attached to 4 other spheres, which are represented by these spheres, which is 1/8 of a sphere. So that gives us a value of 4. Now recall that there's 6 half spheres. The blue sphere is one of them. It's the one on the left. That blue sphere doesn't touch the blue sphere on the right. It's important to understand it. And if you go to Google Images and look up this structure, if you look at it carefully, you see that it's close to it, but there's really some space between these 2 atoms. So I'm not going to count the one on the right. However, it's in contact with the half sphere above and below, so that's 2. And it's also in contact with the sphere on the back and on the front, so that's another 2. So that represents 4 on this sphere. The top, the bottom, and in green I'm going to put the one in the back and in front. Now keep in mind, this blue sphere, that's half a sphere. That's not the whole sphere. The other half is within another cube. So that half is also attached to a sphere at the top and at the bottom, so that's another 2, and then the sphere that's behind it and in the front, so it's connected to those as well. So that gives us a total of 12. And let's not forget these blue spheres that it's attached to. So now you know why the coordination number of the face-centered cubic structure is 12. Now let's talk about the edge length, which is x. Now we know that this part that represents 2r, this is r, and this is r as well. So the diagonal of one side of the cube, that's 4r. So let's turn this into a right triangle. And so we could say that x squared plus x squared, this side is also x, is equal to the square of the hypotenuse, which is 4r. So it's 4r squared. 1x squared plus 1x squared is 2x squared. 4 squared is 16. So 2x squared is equal to 16r squared. Now if we divide both sides by 2, we can see that x squared is 8r squared. And then take the square root of both sides. So x is equal to the square root of 8 times r. So the edge length, x, is root 8 times the atomic radius. So make sure you know that relationship for the face-centered cube. Now the volume efficiency for this structure we said was 74%. Let's go ahead and get that answer. So let's divide the volume of the atoms by the volume of the cube. Now there's 4 atoms per unit cell, and we're going to multiply it by 4 over 3 pi r cubed. And then let's divide it by x cubed. Now we know that x is root 8 times r. So this is going to be root 8 r to the 3rd power. So we have a 4 and then 4/3, which I'm going to write as 4 times 1/3 pi r cubed. Now what is the square root of 8 raised to the 3rd power? So that's root 8 times root 8 times root 8. Root 8 times root 8 is basically just 8. So we have 8 root 8. And the square root of 8 is the square root of 4 times the square root of 2. And the square root of 4 is 2. And 8 times 2 is 16, so this is 16 times the square root of 2, and let's not forget r cubed. So as always, we can cancel r cubed. 4 times 4 is 16, so we can cancel with the 16 on the bottom. So now what we have left over is 1/3 pi divided by the square root of 2. I'm going to multiply the top and the bottom by 3. So this is going to be pi over 3 root 2. So let's go ahead and divide those two things. Now, if you're not getting the right answer, make sure to put this in parentheses. So as a decimal, this will give you 0.7404, which correlates to 74%. So that's the volume efficiency of the face-centered cubic structure. So now you know how to get this answer. Now I want to go over some equations and some conversion factors, more so conversion factors that you need to know when dealing with unit cell calculations and problems. The first one is the conversion between atomic mass units and grams. One atomic mass unit is 1.6605 times 10 to the negative 24 grams. So make sure you know that. Another thing you want to be familiar with is a picometer. Typically, the atomic radius is given to you in picometers, sometimes in angstroms. 1 picometer is 1 times 10 to the minus 12 meters. And 1 angstrom, that's 100 picometers. So that's another conversion factor that you want to commit to memory. And recall that density is mass divided by volume. And the volume of a cube, as we said before, is x cubed. Now typically, in chemistry, you might be given the density in terms of grams per cubic centimeter. But if you ever have to convert it to kilograms per cubic meter, the ratio is 1,000. 1 gram per cubic centimeter is equal to 1,000 kilograms per cubic meter. So 5 grams per cubic centimeter is 5,000 kilograms per cubic meter. Make sure you know that 1 meter is 100 centimeters. So these are some conversion factors that you want to commit to memory. Particularly this one. I think this one's the most important one.